Okay, so this is day 2 for the 6-2 lesson, solving systems by substitution. Yesterday, all the systems that we solved already had a variable isolated. I'm not going to do the warm-up, but we can see here that the y is already isolated, it's already alone, so it's a really good system to use the substitution method on. Same thing in number 2. Y is already isolated in both equations, so it would be very easy to use the substitution method. We can still use substitution if a variable is not already isolated. It's just that we will have to do a little bit of work to get a variable isolated in the beginning. So let's look at example 5. When we look at this system, we can see that neither x or y are alone. But it's simple to get the variable by itself. We just have to get everything else away from it. It does not matter which variable you isolate, and it does not matter which equation you choose to start with. So often, I just look for where is there a variable that already doesn't have a coefficient. I would never choose to isolate this y, although you could do it, because it has a 2 attached to it. But this x doesn't have any number attached, so it really just has a 1 in front. So that would be a really good variable to isolate. Same thing here. This x only has a 1 in front of it, so that would be a good variable to isolate. It does not matter, so I'm going to take the second equation because it's already at the bottom, and I can work right off of it. If I want to isolate this x, that's the one that I want to get by itself, then what would I do to get the minus y away from it? Well, the opposite of subtracting y would be adding y. So I would add y to both sides of that second equation, and my new second equation is x equals y plus 5. You could put the 5 in front of it, but I like that variable coming before a coefficient. Now x is isolated. So it's the same thing that you did yesterday then. Once you have a variable isolated, circle it and put that in for x in your other equation. So we use the second equation. We haven't used the first equation yet. Then I'm going to write that first equation down. It's x plus 2y equals a negative 1. I'm going to take what x is equal to and put it into that equation. So just one additional step at the beginning, you had to isolate that variable. Then the solving process is the same as yesterday's video. So we substitute that in, y plus 5 plus 2y equals a negative 1. So this is what I had to put in for x. And now I'm just going to solve. Y plus 2y is a 3y. To get my y by itself, undo order of operations. Once you have one variable solved for, you're going to take that and substitute it into one of your original equations. Does not matter which one, so choose whichever one is easier. We've used both of them, so it really doesn't matter. Plugging in for y, I would say that the second equation looks like it has less, although I get a little nervous when there's a minus sign and another minus sign, so I might plug it into the first one. It does not matter. Okay, so if I plug it into the first one, I'm going to put negative 2 in for y. Now I solve for x. Final 2 steps would be to put your answer together as an ordered pair and check your answer by plugging that ordered pair into your original equation to make sure that it works. I got 3, negative 2 as my solution. I'm going to skip problem 6. You're going to try it in just a minute. Let me show you 7, and then you can try 6 and 8. So with problem 6, again, you have to decide which variable to isolate. I look for a variable that does not have a leading coefficient. I can see that this y is probably going to be the easiest variable to get alone. Perfect. So I'm going to just write that over here. If I have y plus 6x equals 11, and I want to get this y by itself, I would subtract 6x from both sides. Now I have y equals a negative 6x plus 11. So you're really creating a new system that is essentially the same as your original system. My first equation, I just wrote it in a different form. I have y equals negative 6x plus 11. And my second equation, I'm going to keep exactly the same. 3x plus 2y equals negative 5. Just like we said in our steps, you have a variable isolated, circle what it is equal to, and plug that into your other equation wherever you see a y. So all of this is going to go in there. So I'm going to have 3x plus 2 times, what are you putting in for y? We're putting in negative 6x plus 11. Now I have one equation with the same variable, so I can solve that equation for the variable x. So I'll have 3x plus, I need to distribute first. Oops, sorry. Really, a positive 2 times negative 6 is going to be a minus 12x, so I'm going to just change that to a minus sign. Plus 22 when I distribute. Combine like terms. Isolate your variable. Once you have one variable solved for, always plug that back into one of your original equations. I would recommend you going all the way back up here. Use one of these, because just in case you made a mistake in this process over here, we want to make sure that x works in one of your original equations. It does not matter whichever one you think is easier. So I'm going to put it into the first one, because I think I like 11 better than negative 5. So I'm going to have y plus 6 times, instead of x, I'm going to put in a 3, and that's going to equal 11. So again, where did that come from? That came from this original equation right here. Now solve for y. Last step, put your answers into an ordered pair form and check your solution. Plug those values back into your original equation and make sure that they work in both. That if it does work in both parts of your system, then it is the solution. So try 6 and 8, pause the video, and then press play to see the answers. If you need to make corrections, use my work to correct it. So here's problem number 6. You may have solved it a different way, but I chose to isolate x in my second equation. Even if you chose to isolate y in the first equation, your answer should still come out to 3, negative 10. Make sure you plug that in to check it. It does work out. 3, negative 10 does work in both equations. So if you did not get 3, negative 10, I would erase your work and write down this work that you see here, or try to find your mistake. And problem number 8. Again, you may have chose to solve for a different variable or a different way, but I chose to solve for y in my first equation because there's no coefficient. And when I solved, I got negative 1, 6. If you plug it back in and check, it does work in both equations. Okay, so let's try a word problem. I'm going to try number 9. An iPhone repairman charges $45 consultation fee, so that's just to come, and then $20 per hour of work. So I could say that he charges, or y equals, it's a $45 fee to start, plus 20 per hour, that tells me multiply, of work. Right now, I should be defining my variables. It's 20 per hour, so x stands for the number of hours. And this is all being added to 45, which is going to give us our what? It's going to give us our total charge. Another iPhone repairman charges $30, and that's just the flat fee, plus 26 per hour. And that's going to give us the total charge there. So both equations involve y being the total charge, and both equations involve x being the number of hours. Put your big bracket on there to show that this is a system of equations. They go together for this problem. Perfect. So now solve this system. This is a great substitution problem because we can take this right here and put it in right there. So when I solve, I'm going to combine my x's on the side that there are more of. And I'm going to isolate x by undoing order of operations. So I had to think about that a little bit. 6 goes into 15 twice. That gets me up to 12. I have 3 6 left, or half. So it's 2.5 or 2.5. Now I can plug that into one of my original equations. It doesn't matter which. $20 times 2 is 40. 20 times a half is 10. 40 and 10 give me 50. So it's a nice way to do it without a calculator, although you can use one here. So we get 95. So answer the questions. For what number of hours will the total charge be the same, and what will that charge be? So I would say after 2.5 hours, both will charge $95. It's nice if you have a word problem to end with a word answer. So I like to see a sentence at the end of the word problems. Try the next word problems and then press play to see the answer. If you have questions, please ask in school. Okay, so for problem number 10, your system should involve 2 equations. The first equation here I set up to relate to the number of quarters and dimes. So I know total I have 8 coins. So the first equation represents that. The second equation, all of these numbers relate to how much the amount of money is. So each quarter is worth 25 cents and each dime is worth 10 cents. And when you add the amount together, total, you would get $1.25. If you have questions, please ask them in school, but I just want to show it to you in case you did try it on your own. Then you could solve for x or y. I solved for x first from the first equation. Then I substituted that into the second equation, and I solved. Now, you could get rid of these decimals by multiplying this whole equation by 100, but I don't want you to be scared to work with the decimals. Once you solve for y, and I had to carry my work over here, I got y equals 5. Then I would plug it back into one of your original equations to find x. Definitely the first one is going to be easier than the second equation. So I figured out that she must have 3 quarters and 5 dimes. And at the pet store, for the pet store problem, I set up my system like this. You may have solved for a different variable over here. Either way, you have a little bit of work to do because you have decimals. But in the end, I figured out that each bowl must cost $2.50 and each bone must cost $1. Again, please ask questions. These word problems are great applications for systems that occur in the real world and how they could be useful to you. So you want to make sure you practice them and get really good at these word problems.